All right, so I want to make a short video about how set theory is, in fact, the foundation of all of mathematics. I kind of mentioned this when I was talking about proof and the importance of the idea of proof and how mathematics is made up of these things called theorems that are all sort of stacked on top of each other with this nice logical structure that kind of like supports everything. And it's all based on some axioms. And the axioms of mathematics come from set theory. So, a little bit of history that I put at the bottom here. First of all, set theory was pioneered really in the late 1800s by a fellow named Georg Cantor. Cantor is a pretty famous mathematician, and he published a paper in 1874 that really laid out the sort of initial framework of set theory. This type of set theory developed by Cantor has come to be called naive set theory because it had a few problems with it, but they didn't find that out for a while. So in the late 1800s, this was further developed by some other mathematicians like Dedekind and Weierstrass. Dedekind did a lot of work in particular in sort of developing a way of defining the real numbers that was a little more natural and easy to work with. So then in 1900, an English fellow named Bertrand Russell, actually, as well as another mathematician, kind of independently both came up with this paradox. It's come to be known as Russell's paradox. And at the time, based on Cantor's set theory, it was valid to define a set like this. S is equal to the set of all sets X. So in this case, X is a set, such that X is not an element of itself. So at the time, the rules for set theory were relatively loose, and a set could be an element of itself. I did mention before that sets can be elements of other sets. Well, if a set can be an element of itself, you could say, let's define a set like this. And then the question is, if you define it as a set of all sets that are not elements of themselves, the question is this set an element of itself? Because if it is, then it isn't. But if it isn't, well, then it is. And this produces this backwards, back and forth kind of paradox. And it's a true paradox, not just something that sounds unreasonable, but something that truly is impossible, like a contradiction. And so this essentially poked a big old hole in the entirety of set theory and made everybody freaked out. Because if you have a bunch of things that imply something which is paradoxical, then it means that they themselves were in fact not true. So Zermelo and Frankel were two mathematicians who about 20 years later independently worked on some things and ended up coming up with a set of axioms, which were then combined with something called the axiom of choice, which was developed actually much earlier, I think actually by Cantor himself. So the axiom of choice combined with the Frankel and Zermelo axioms produced what we now call the Zfc Axioms, and this essentially fixed mathematics. So there was this period of 20 years in the early 1900s where mathematicians were freaked out because they thought everything they had done was a lie. But then somebody fixed it, and they figured out a way to justify everything more rigorously, and they patched up the problem with the paradox. And created what are now still remain the sort of fundamental axioms of mathematics. Potentially, there's more than one set of axioms that can serve as the fundamental axioms, but this is the most commonly accepted one that we have in mathematics. So I'm not going to go over those axioms; they're pretty complicated, and you have to really take a whole class in this to understand that stuff. But I did want to show you one thing. So coming back up here, I want to show you one thing that kind of gives you an idea of how it is that mathematics is entirely based on set theory. And that is the definition of the natural numbers in terms of sets. So before we define numbers at all, before numbers exist, there are sets. And the very first set that can exist is a set with nothing in it. So we are going to start from the empty set and literally create all numbers. At least this is the beginning of them. So the definition is actually recursive definition. So it has two parts. The first part says, let's have 0 be the empty set. Okay, so in this context, we're actually saying that 0 will be defined as the empty set. Normally, we might think of those as separate things, and for most purposes, we do think of them as separate things, but when you're strictly defining natural numbers, they're equal to each other. And then the second thing is that for n greater than 0, we're going to define n to be equal to the set of all natural numbers preceding n. So up to n minus 1, like that. So this is what this gives us. This gives us 0 is an empty set, which looks like that. Okay, and then 1 would be equal to the set containing 0 and 1. No, sorry, I misspoke. 1 would be the set containing 0, because 0 would be n minus 1, right? So it's all natural numbers preceding it. So this is going to look like a set containing nothing. Get ready to see a lot of braces. Okay, 2 is going to be the set containing 0 and 1. There we go. And so that's going to look like a set containing nothing, and a set containing nothing. Like that. Now, you'll notice the cardinality of this set is 0. The cardinality of this set is 1, because it has one thing in it. The cardinality of this set that defines 2 is indeed 2. So technically these numbers, natural numbers, are defined before cardinality in the logical structure. So, but it does happen to be the case that once you define cardinality, the cardinality of these sets does correspond to the number that they define. I'm going to do one more of these. Because it starts to get pretty long. So 3 is the number, the set containing 0, 1, and 2. And so that would be the set containing 0, which is nothing, like that. And then 1, which is this thing. And then 2, which is the previous one, which is this. Oh my goodness. And there we go. And that's 3. So it has 3 elements. It has 0, 1, and shoot, and 2, like that. And I'm not going to write 4 because it's going to be pretty long, and 5 is a lot. I mean, 5 would take up like 3 lines. So that's how you define natural numbers. And so as you can see, this gives this crazy structure that's essentially just a bunch of braces, right? Because everything is being built out of the empty set and then sets that contain the empty set and so on and so on and so on. So in a way, this is like numbers are created out of nothing. And I think that's just beautiful. Now, this is just natural numbers. You would then go on to define how negative numbers are going to work. And then there's this thing called Dedekind cuts, which take integers and then produce, you first make rational numbers. And then you can make real numbers from rational numbers by doing Dedekind cuts. And then once you have all the real numbers, like you can define operations in terms of sets and set operations, which we're going to learn actually in section 2.2. So this is just the beginning.